Hello everyone. So today we will talk about the design of linear phase FIR filters. So not any other FIR filter. We will be specifically talking about linear phase FIR filters, which are of commercial interest in speech and audio applications. That too, we are talking about a method called as windowing method. So there is one more method called as frequency sampling method that also we'll be discussing. For the time being, the topic is not just any other FIR filters, it is the linear phase finite impulse response FIR filters using windows. So in today's class, we will talk about the reason why the frequency response of the filter looks peculiar. One thing. Second thing is making it from theoretical to something practical. As you might have understood that this theoretical impulse response is not possible to be implemented in reality. Third thing is what is the need for windowing and what is windowing. So these three aspects I will be covering today. Okay. So let us get started. So what is this windowing thing? So before that, let us see how a typical response of a filter looks like. So you all might be wondering this particular term that is coming e to the power minus j omega alpha, or the phase that you got, right? So you might remember in one of the class where I was giving you an introduction about the topic, I had drawn this particular thing. Wait, if it, okay, yes, here it is, right? I told you that this is the magnitude and this is the phase response. That means this hd of omega, you can see, is a complex quantity. The desired frequency response, this is what you need, you are claiming. You want a frequency response which is having magnitude 1 in the passband. Magnitude 1 in the passband, what does it mean actually? It means that you want every input to go to output without any attenuation. Y of n equal to 1 into x of n, you can say. It's a linear thing, right? And it's a constant. Okay. So whatever you give as input, same thing will go to output. And after the cutoff frequency, you have 0. That means y of n is equal to 0 into x of n. So that would be 0. But the important thing here is, where does this, okay, 1 is fine. Where does this phase thing come into picture, right? Where this phase with this particular slope come into picture? Can't we may have a impulse response which is having a frequency response that is real? Okay, so that means phase, making the phase 0. So what is making the phase 0? Listen to this. Making the phase 0 means you are trying to make the output input reach output with 0 time delay. Okay, so that doesn't seem to be practical. But anyway, let us see what is the catch involved and why the response looks something like this. Okay. So let us go to the topic at hand. So usually when you specify the frequency response as the desired one, you usually start with this particular thing. hd of omega should be equal to 1 in the passband. Now this particular thing here is not part of your strategy. Okay. And then you start, okay, you got this impulse response, right? So what is the method? You start with the frequency response, take IDTFT, and there you get your impulse response. Okay, fine. There you get your impulse response. Okay. Now there is a catch involved. Okay. So here this is a very cute looking impulse response where you have it starting from minus 20 go till plus 20. But if at all you have really studied in the previous semester, or if at all you take a sample and try to simulate it, you will understand that this particular thing is not of finite duration, but usually it is having an infinite duration. The ripples here, right, the slow side lobes, they keep continuing till infinity. They usually keep continuing till infinity. So what you have to do, that is first thing. For the timing, let us concentrate on the first thing, the introduction of the phase term. Okay. Now see here, for the timing, let us understand that, let us assume that you have stuck to having, okay, say there were values here. Okay. So this would have gone on to infinity on either sides. This would have gone on to infinity on either side. Say you chose some finite values. Okay. Say you chose some finite values and made it a FIR filter. Okay, say you made it as finite values. Then afterwards, say, now there is a catch involved. So this particular thing you can see, the impulse response is having values on the left side, which indicates future. That makes the entire impulse response as non-causal. Non-causal things cannot be implemented. Okay, non-causal things cannot be implemented. So how shall we make this causal? How shall we make this causal? So a good idea would be, we shall push this thing to the right side. Now let me ask you, what is the order of this particular impulse response? I had told you order is the number of D flip-flops that you need to implement this particular system with inputs and outputs, right? Remember the difference equation implementation which I had introduced in the previous class. So here it is nothing but count the number of values, non-zero values in impulse response, in continuous. In between these zeros shall be counted. So you can see in this particular thing, there are totally 41 values in this particular system. There are totally 41 values. Okay, so the order of this filter is 41. Okay, this is a order of this filter is 41. Say now to make this thing causal, what you have to do? Okay, order is 41. To make this thing causal, what you have to do? You have to push this particular thing from the left side. You just have to push this thing to the right side till all the values on the left side vanish. Till all the values on the left side vanish. Say something like this. Let me try. Okay, say something like this. Now you have all the values on the right side. Okay, now this is bearable. We don't know what happened. Nothing has happened. The response is intact. Only thing is, you have introduced a shift in the time domain. You have introduced a shift in the time domain. Now this can be equivalent to, now your entire axis being moved here, so that the value here, this is your new origin. That means by how many values you have to move this thing to the right side? If at all order is, say 41 was the order. So you have to move this thing by 20 locations to the right side. So that number is 41 minus 1 whole divided by 2. Got it? Got it. Now a shift in the time domain. You studied this also, right? The time shift property. A shift in the time domain introduces a multiplication by an exponential in the frequency domain, right? Remember. So by what factor did you shift? By factor n minus 1 divided by 2, right? N minus 1 divided by 2. Now this thing is introduced here as alpha, okay, which is nothing but the slope. Now we got this particular thing. So this particular slope, whatever you tell in the frequency domain, is nothing but a shift in the impulse response, which you yourself introduced to make the entire impulse response causal, so that the actual thing can be implemented in lab. Okay, so that explains why in your desired frequency response, the phase is not 0, but it is 1 in e to the power minus j omega alpha. Okay, so that explains alpha. Okay, okay. So this is one thing. Now let us talk about what is the next issue at hand. Okay, so that is where if at all you start with only the desired frequency response, something like this 1 from minus omega c to omega c, say from minus omega c to omega c, if it all has started, this is what you would have got as the impulse response. Very symmetrical thing. Okay, a symmetrical thing about the y-axis, symmetrical thing you would have got, non-causal definitely. Now that you shifted it, by what factor? Say your order is m, then you shift it by factor m minus 1 into alpha. See this, every n replaced by n minus m minus 1 divided by 2. Sorry, I told it as n, right? So here author has taken it as m, whatever the number of values in the impulse response. So there you get this particular template of a typical low pass linear phase FIR filter. Remember linear phase. Now let me just remind you that linear phase filters are those which are symmetrical about the midpoint. Okay, now that you shifted it, is it still symmetrical? Yes, of course, it is still symmetrical. Symmetrical not about the y-axis, remember. Symmetrical not about the y-axis, symmetrical about the midpoint. Okay, that's that. Okay, now here also it is symmetrical. There is some midpoint also here. So this is also still symmetrical, but now there is phase introduced. Okay, now next thing, that is our problem. Now what next happens? Now choosing the order. Now I told you the first thing we solved. Now I told you that what should be my order, how to choose an order, because as I said, if at all I take the inverse of a rectangular pulse, you usually get the impulse response with infinite values. These values here, they go on. You can keep calculating them. You want 100 values, you get 100. You want 1000 values, you get 1000. Of course, the amplitude keeps diminishing, but the values are there. But then you have to decide how many values are. Are you happy with 10 order? Are you happy with order 20? Or you may want an order of 50. Now, how to choose the order? Or how to choose the order? Let's talk about. Okay, say I settle by an order of, say, 21. Order has to be odd. Okay, order should be odd because there is always a midpoint involved, right? There's always a midpoint. Values on the left side, same number of values on the right side. That explains an order which is odd. Okay, now say I have a budget for an order of 21. That means I need to pick the values somewhere around -10 to +10. Okay, somewhere around -10 to +10. Okay, say now let me go to what, a whiteboard. Let us see. Here, let me go to whiteboard. New share. Yeah, there I have a whiteboard. Okay, so say now let me start from, wait a second, let me see if at all I can get a straight line. Okay, now say I have a filter, symmetrical. Okay, so what I have to do is, now suppose from the midpoint, okay, say from the midpoint, if depending on my budget, whether I can afford a 10th order filter or a 20th order filter, I have to choose wisely. Okay, what is the deal with a 10th order filter and a 20th order filter? Now I know this is a recorded video. Okay, so let me fine tune this. Okay, a filter of order 11 and a filter of order 21. I will give you some 20 seconds to think which filter is better and why. What are the advantages of a filter with order 11 and the disadvantage of filter with order 11? Then what are the advantages of filter with order 21 and what are the disadvantages of filter with order 21? Okay, so I will give you time, think. Okay, okay, I got some values. Now let us go to the topic. I understand this is a video. You can even pause and you can think. Okay, so the task is, now what you have to do, say your order budget is 11, order budget is 11. Then what you have to do, from the center, 5 values on the left side, 5 values on the right side. Okay, if at all your order budget is say 21, then what you have to do, 10 values on the left side, 10 values on the right side. If at all your budget order is say 31, then 15 values on the left side, 15 values on the right side. That's it. Once you get this particular values done, then what you have to do is push it by that particular factor. So to get an origin on the 0, okay, the first value on the 0, okay, and make it causal, okay, and make it causal. Okay, now this whole thing of picking the finite values is called as windowing. Okay, see, your impulse response had infinite number of values, but you make sure that the response is symmetrical and you pick from the center, you pick values, finite values on the left and the right side. Okay, the entire process is called as windowing. Entire process is called as windowing. Now let me take you to the page where author has to put his own inputs regarding choosing the order of filter. Okay, so what he has to say, so what author says is, I'm using too much of this author thing here, right? Okay, so larger order of the filter will produce better sharp cutoff characteristics. Okay, so I think we have studied this in an introductory topic on the filters, where I was telling you an ideal filter usually needs an infinite order, right? Even right from calculating this Virat Kohli's average to your marks, the more previous semesters we refer, the more better judgment we can make on you. The more previous year's records, okay, more previous innings scores, if at all you see of Virat Kohli, you can judge him better. So say a first order filter is say something like this, very sluggish. Second order filter will be little better. Third order filter even better. Fourth order filter good. An ideal filter will have an infinite order. See here, author has compared here a 31st order filter and a 61 order. You can see 31 order filter is sluggish, takes a lot of time to decay from the pass band to stop band, whereas a 61 order filter is much faster. Let me use a different color. This one maybe. Okay, okay. 61 order filter decays much faster. Okay, 61 order filter decays much faster. That means, let me just take this particular thing. Say you implemented a filter. Okay, say here was your cutoff frequency. If at all I use say a filter of order 11, say it might be something like this, decays slowly. Say decay. Say this is my filter with order 11. Then if at all go for a filter with order 21, say from the cutoff frequency, this decays faster. Okay, order with filter with order 21 decays faster. Okay, filter with order 21 decays faster. So from the performance point of view, if at all economy is not your concern, you are only into performance, then higher order filters are always better because they produce the sharp roll of characteristics. Okay, sharp roll of characteristics of the transition. Okay, so I was telling you in the previous class, there is something called as the pass band, there is something called as the stop band, and then there is something called as a transition band, right? Then there is something called as a transition band. See here, right? This is what I was referring to. So ideally the width of the transition band should be 0. Ideally, it doesn't happen all the time. So a first order filter will have a high transition band, whereas a second, third, fourth, fifth, sixth order filter, as and when the filter order, increase, the width of the transition band decreases. So ideally it should go to 0. So ideally order shall go to infinity. But then there is a catch involved. So higher the filter order, here you can see, higher the filter order. See here for this particular case, whatever is in the filter order is, say, if at all there are, wait a second, let me take a better example. This is a generalization. Okay, okay. Now see here, this is a filter referring to n minus 2, n minus 2. See here, filter order means higher the order, more number of D flip-flops. So if at all I have a second order filter, say second order FIR filter, it will have 1 D flip-flops, then afterwards 1 more D flip-flops, then in between there will be some combinational circuitry, of course. In between there will be a combinational circuitry, and then you will have your output coming. So the time between the input and output here, you can see it will have a delay of 2 clock ticks. When a valid input is given and for a valid output to come, there will be a delay of 2 clock ticks. Whereas if at all I go for a fifth order filter, between the input and output, how many D flip-flops will be there? There are going to be 5 D flip-flops. That means when you give the input, by the time you get your first valid output, there will be a delay of 5 clock ticks. Okay, so a higher order filter may be giving you a better frequency response, but then its response is sluggish. I should say, not sluggish, it is giving you a constant delay. It's giving you a constant delay, which is very much higher. Okay, sorry, not y, n minus 1 is not there. Okay, I will just concentrate this. A second order filter results in an output which is delayed by 2 clock ticks, whereas a fifth order filter results in an output which is always delayed by 5 clock ticks. So higher order filters are costlier. See, higher order filter, filter of order 10 needs 10 D flip-flop. Filter of order 20 needs 20 D flip-flop. So higher order filters are ideal. They are much better, but then they are much costlier due to more number of D flip-flops and much slower due to a large delay when input is given and first valid output is required. Okay. But then when you need performance, you cannot think about budgets and all. Okay. And little bit delay is also fine when you are into a particular frequency requirements. Okay. A particular frequency requirements. Okay. So a typical method, as I told you, is this particular thing. You get the impulse response. Okay, you get the impulse response, which is of infinite duration, something like this. You get an infinite duration, something like this. Then afterwards, what you do is, then you decide to stick to finite number of values. Okay, out of this particular. Now this is discrete in nature. So say I decide to choose some 21 values here. Then the entire process, I will call it as windowing. That particular entire process, I will call it as windowing. So what is windowing? Windowing is nothing but, say, for example, let me come to this particular page. Now let us assume that I take a function w of n. Let me call a function w of n. It contains, what does it contain? Say 1, 1, 1, 1, 1, 1. Okay. 5 values on the left side, 5 values on the right side. Amplitude is 1. So when you multiply this with this, what's going to happen? These amplitudes are all 1 only. So when you multiply this with this, I get all the values. Origin, 5 values on the left side, 5 values on the right side, as they are. So everything in this particular window can be seen. Okay, of course, you shift them afterwards and you make it causal. So this entire process of picking finite values from the impulse response is called as windowing. Okay, it is called as windowing. Okay. So here, that's what author refers to. So once you move the impulse response to the right side, you multiply it with this function w of n. See, this is what I was talking about, windowing. It will be 1 in that particular duration where you want to pick the impulse response as it is. Okay. So that's why your actual impulse response, h of n, will be nothing but whatever the impulse response you got by taking the IDTFT of the frequency response, and then you pick the finite values. Picking the finite values is called as multiplication by rectangular window. Okay, multiplication by rectangular window. So what you are basically doing, is you are taking this particular thing, simply cutting off the values on the left side, values on the right side, and picking the values in the center. Okay, abruptly cutting the values on the left side and values on the right side. Not a good idea. It's not a good idea. When you do that, this abrupt truncation is causing a problem. The problem is called as Gibbs phenomenon. It's called as Gibbs phenomenon. The abrupt termination, what it does is, when you implement filters by cutting them, so two things happen. One is, you are now making a compromise. Now your frequency response is no more ideal. It's not the box what you saw, because now you are not going for infinite values of the impulse response. You have made them finite. Then you have made them causal, right? You push them to the right side. So that will be seen as a that will be having a consequence in the phase response. But then once you make them finite, once you cut them, cut the values on the left side, cut the values on the right side, what happens? There will be ripples in the pass band, which will be more pronounced. These ripples will be more pronounced at the band edges. See here, suddenly whenever there is supposed to be a transition band, you have an overshoot happening. Whenever they here, see the values in the stop band, they are supposed to be suppressed, but then there is an undershoot. Now see, this is a magnitude. Okay, that is why magnitude of a square of a negative is a positive quantity. That's why we have the values on the top, but it's actually, it's a oscillatory behavior. This is not a desired thing, especially when you are supposed to reject something. There is an overshoot coming. No, not a good idea. So this particular thing is called as Gibbs phenomenon. So what do they say? Oscillatory behavior of the response near the band edges. Why does this thing happen? You suddenly terminate the values on the left hand and right hand side of the impulse response. So not a good idea. So that's why what they say is, you want to terminate, you do it in a manner, so that the windowing shall have a taper. What is this taper thing? Now say what author is trying to say is, if at all you have, see, selecting the values from the left with a magnitude 1, selecting the values on the right with magnitude of 1, then suddenly cutting off the values on either sides. No, not a good idea. Instead, what is the better idea is, what you do, you let us have a taper, let us have a gradual change in amplitude. Say you have 1, then 0.9, then 0.9, okay, 0.95, then 0.9, then 0.88, then 0.86, and so on. Gradually, let us do this particular thing. Okay, you go for a higher order, but do this gradually. Okay, now see here. Now, since this is a very slow transition, okay, now see there is a smoother cutoff, and you don't know when actually this thing happened. So no abrupt termination, but there is a taper in the window. So as I said, what is windowing? Window is picking the values, finite values on the left and right side, but you don't do it abruptly. Rather, you don't call it with all ones. Okay, no all ones now. Okay, no ones on the left and ones on the right side. Rather, you have gradually changing amplitudes in the window function. Because why do we do that? Because we did not want this, because we want to avoid this particular situation, the overshoots and the undershoots near the transition band. Okay, so windowing, other than the rectangular thing, picking the finite values is not ideal. So you should rather have something which is tapering in nature. Okay, so let me show you how does it work. Okay. So see here, a typical rectangular, when you say, is the impulse response will have ones actually throughout the entire function. Okay, from 0 to say order 21 or 31, whatever. The entire duration you will have all ones. Instead, if at all you want to have something smoother, okay, say here, see this particular thing. Okay, so here the amplitudes are not ones, 1, 0.9, 0.8, 0.7, 0.6, and so on. So people have worked on this, and they have found out that the different shapes of the windows give different advantages and disadvantages. Okay, so all these windows, they come with a function. See, there is something called a Blackman window, Hanning window, Hamming. No window is nothing but rectangular window. You know, those one. There are so many. Each are having their own advantages and disadvantages. How do they differ from each other? So let me show you here. So here is an example of something called as a Hanning window, and there is something called as a Hamming window. And how do they differ? You can see here from the pass band. See, 0 is the attenuation in the pass band. 0 attenuation is cool. 0 attenuation means whatever you give as input, same thing will go to output. But then between the pass band and stop band, see this particular attenuation here. This number is around something like 40, whereas that number is something like about 50. Got this particular? This is how the windows differ from each other. Let me compare them now. Here. You can see here, if at all I, from the FIR filter, from ideal one, I will multiply it with a window function, and I will use a no window, or say the rectangular window. What's going to happen? Between pass band and stop band, there will be a transition band, and the between pass band and stop band, okay, so the pass band attenuation, and between the lobe of the first stop band, the gap will be only 21. Whereas if at all I go for something called as this Hamming window, if at all I implement, you can see the slope is something like 40 between pass band and stop band. That means pass band, 0 attenuation. In the stop band, so what is called as stop band, you calculate, see, these are actually, there are oscillations, but what matters to us is the height of the first side lobe. Height of the first side lobe in the stop band matters. So this is around 44. This is around 44 between pass band and stop band. Same thing for a Hamming window. You can see the same amplitude between the pass band and first side lobe in the stop band. It is something like 53. Now I want you to think that passband attenuation is 0, input to output, and stop band attenuation is one of the window is 21, another window is 44, another window is 53. Which window is better for us? Ideally, let me tell you, the stop band attenuation, ideally it should be infinity. Ideally, the stop band attenuation should be infinity. So rectangular to Hamming, I think as and when you are progressing here, Blackman is doing much better. Hamming, okay. Hanning, okay. Rectangular, very, very average. Rectangular was the simple one. Simply take the values on the left side and right side. You can see. Now that we introduced the taper, this particular shape, while we selected the values in the impulse response, you can see our filter responses are getting much more ideal. But then there is a catch also. You can see the response between the pass band and stop band, the transition bandwidth is, it keeps on getting wider. Okay, your attenuation performance is getting better, but then your sideband suppression performance is getting poor. Okay. So refer to the textbooks and read these things on your own and have your own comparison between which windows are better and which windows are bad. Okay. So let me stop this thing here. It's a video. If at all you get doubts, you can again scroll it on the left and right and you can get them solved. Textbooks are there for help. Let me stop here. Okay. Bye.